Yusu. So it is my great honor to introduce to you Yusu Wang. She obtained her PhD from Duke University in 2004, winning the Best PhD Dissertation Award at the CS department. She was then a postdoc at Stanford, and then for many years a professor at Ohio State University. She recently joined the University of California at San Diego. In her research, Yusu brings together geometry and topology, both computational and applied, mixing ideas from the two domains for the benefit of both. Yusu received several important awards, such as DOE, and several Best Paper Awards in top-tier conferences. Yusu serves as an editor of prestigious journals, such as SciComp, Siam Journal on Computing, and JOSAGE, Journal of Computational Geometry. 2 years ago, I had the pleasure of co-chairing with Yusu the program committee for SOSAGE, the Symposium on Computational Geometry, the leading symposium. It was half a year of a very intensive cooperation, during which I came to know her not only as a great researcher, but also as an extremely nice person. Let me also mention that Yusu is my academic niece. That is, her PhD supervisor and I share the same PhD supervisor. Yusu will tell us today how to analyze graphs in a combined topological and geometric manner. Yusu, the stage is yours.
Thank you. Thank you, Gil, for the wonderful introduction, and thank you for inviting me. It's really great to be able to give you to tell you about my research, and I wish I could be there in person to interact with you physically. We'll do what we can. Okay, so I want to talk about some of my recent line of work on using a topological and geometric method for different data analysis, analyzing different type of data, and particularly I'm going to focus on graphs today. And so let's take one step back about first what is why we care about the topological and geometric data analysis. Well, and for this audience, I think really I don't have to sell why geometry. I mean, we all understand that for a long time, geometry has been the language starting from Pythagorean theorem, Euclid's elements. Geometry has been the language to help us to interact with the world, to model what we see in the world, and so further to analyze, to analyze it. Now, about 100 years ago, there's a new kind of geometry called topology that come into picture and received a significant development. Now, by ignoring the detailed geometric information, but instead focusing on something coarser but potentially more essential as characterized by connectivity, topology also gives us ability to also model what we may not, the structure that we may not easily see of the space around us. Okay, like in this example, this is a common example where the donuts and the coffee mug, they don't look the same, but they share something in common, which is they both have the hole in the middle, and one can continuously deform to the other without ever stitching or breaking things, and vice versa. Okay, so in fact, the power of the topological method is not just that it can tell us how many holes there are in the domain, in the object of interest, is that it also gives ways to also analyze not just the space themselves, but also functions and the maps defined on them. Okay, so at the same time, we now see a massive amount of data, not just 2 or 3 dimensions, but also high dimensional data. But this data, they're not generated randomly. Data has structure and shape behind them. And this structure and shape often are essential to their understanding. So just think about the cluster structure that's very common in many applications. So to this end, obviously, geometry and topology form a natural platform to help us to make sense of them, to process them effectively. Okay. And I work in something called TGDA, which is combining this mathematical objects and the concepts and computational algorithm together to develop efficient methods for data analysis through this topological and geometric sense. Okay, but of course, I mean, this audience, they've done a lot of using geometric methods. And what I want to perhaps due to this, that to focus a bit more on the topological aspects, okay, I'm going to use graph type of data as example to show you how geometric and particular topological ideas can come together actually to help us in such tasks. In particular, the first thing I'm going to spend most of the time talking about reconstructing geometric hidden graphs from data. Okay, I'll give you some motivation and algorithm and some theoretical understanding we have. I will very briefly also mention comparing and classifying abstract graphs, not necessarily geometric graphs, and also to retrieve shortest path metric from noisy observed graphs. Okay, all right. So first is the graph reconstruction. So the problem is simple. We have some type of data, could be point clouds, although later we're going to first start with a density field, sampled from a hidden geometric graph, which is embedded in the geometric space, like this red one that I draw here. And the goal is to reconstruct another graph, this blue one, for example, that approximates the hidden graph that we don't see. Okay. And we hope to get also certain guarantee about the faithfulness of this blue reconstruction. Okay, so here's a more concrete motivating application. Let's say that we're given this GPS traces, GPS trajectory. Just think of them as a bunch of polygonal curves sampled from, you can think of this GPS traces as a sampling of a hidden road network of a city that we don't see. Okay, so that's a blue trajectories on the left, and our goal is to recover the hidden road network from these trajectories. Now, this problem itself has attracted a lot of attention, partly because of the abundance of GPS traces that we can obtain nowadays. Okay, there's some challenge in particular. Other than that, the GPS traces could be noisy, say in the city area. A bigger issue is that such sampling are typically highly non-homogeneous. So you could have the downtown area that receive many more traces compared to the residential area, or even in geometrically close location, you could have a large road, a major highway intersecting with a small road, and the sampling here can be very non-uniform. Okay. And a lot of previous methods typically relies on local information to help to make decision whether this point is at the junction nodes or it's on the road and so on. Okay, or they may also involve some thresholding to decide what is signal, what is noise, and such a local information make figuring out the precise graph topology connectivity, such as junction nodes and how they're connected, much more challenging. So what we're going to do is that we're going to use the topological concept from Morse theory to help us using this global information to help us to decide what's the connection of the roads, and this make the approach, because we're using the global information instead of making local decisions, this make the approach more robust against noise, small gaps, and particularly the non-uniform sampling of the traces. Okay, you'll see later that the algorithm conceptually is very simple, very clean, and easy to implement as well. Okay. Now, but before I move on, I should point out that using the Morse theory to uncover the hidden structures, not necessarily graph structure, but also potentially higher dimensional sheets and so on structure, this idea is not new, and I have the reference here below, starting from Goulas' PhD thesis. Okay. All right. So what's the idea? Well, we're given the GPS traces, but let's first assume that I can convert them into a density field, convert them like for each of the GPS traces, you can just sample it many times, then you can take them as a point cloud sample and then do a kernel density estimation. Okay, so now let's imagine that what we're given as input is a function, a density field, F, defined on your domain I. This I can be high dimensional domain, but for now, for visualization, just stay in 2 dimensions, okay? But it can be high dimensional domain as well. Okay? And in this picture on the right bottom, what I'm showing here is the graph of this density function. Okay, so the density field is higher around the hidden road, and so and the lower off the road. Okay, Now we look at this graph of the density function, and we can treat this as a terrain, as a mountain range, okay? And intuitively, the mountain ridges of this terrain, this is where locally the density is kind of high compared to when you go off the road, okay? They kind of capture where the hidden road might be, okay? And this is exactly what we're going to do. And to capture this mountain ridges of this terrain, we're going to use something called one unstable manifold of a function from the Morse theory. So what is it? Well, so here's a very brief introduction only of the relevant parts. So let's assume that our density for now is a smooth function, okay? And it also behaves nicely, so-called Morse function. Now, here I'm showing the graph of the function again. Given a point in your domain, so here I'm showing x on the graph of the function, the gradient of this function is basically the steepest descending direction of this function. Okay, so it indicates the largest rate of change of the function, the direction with the largest rate of change. I should point out this usually gradient is the steepest ascending. Here I'm inverting the direction so I can talk about the water flowing down. Okay, so this is actually, as I said, this is actually the direction that if you imagine you put a drop of water on the surface of this mountain, this is the direction where the water will flow down. Okay, and if you let the water flow down and continues and track this trajectory, you get this, what I have here is a dotted curve here. This is the so-called integral line. You can think of this essentially as a flow line. Okay, and you can also assume the water goes up, then you also the flow line also extend upwards. Okay, so ultimately this flow line intuitively is a maximal line where the water, the trajectory of the water can form. And when would this water flowing stop? It stops when you are at a point where you don't have gradient anymore. Your gradient vanishes, becomes zero. Okay, like in this case, it will stop in this minimum, local minimum V1 here, and this points without gradient, they are exactly the critical points of your function. Okay, so in this example, since it's two-dimensional function, we have three types of critical points. We have minimum, the blue one, maximum, the red one, and we also have saddles. Okay, or more precisely, the saddles of index 1. Okay, now generically, this flow line, your water, usually will flow into a minimum, okay? But sometimes you have this integral line, this flow line, it kind of starts from maximum, but then ends at this saddle point, okay? And this is necessary because if you imagine that you put a drop of water on this side of the mountain, then you're going to flow into V1. But if you put it on the other side of the mountain, you're going to flow into V2, and then somewhere in the middle, there's going to be a transition. That's where when this flow line flow into the saddle point as here, okay? And this kind of flow line, they're called the one unstable manifolds, okay? They go from maxima to saddle, or in general, it's maxima to the so-called saddles of index d-1, and then to maximum. So together, it's like a mountain peak to saddle, mountain peak to saddle, and then together they form this mountain ridges, separating basins, okay, separating one minimum from another minimum, okay? And that's why intuitively we're going to use this one unstable manifold to capture the mountain ridges, which further to help us to identify where the hidden road networks are. Okay, so this here's an example on the trajectory data, on the real data. So that was the intuition. And we use one unstable manifold from the Morse theory to help us to capture the hidden road. But in practice, we do not have this nice smooth manifold with smooth function defined on that. Okay, so usually what we have a piece as a linear approximation of the domain, like in this case, a triangulation, and the function value is only available at the vertices of the of your domain of the triangulation. Okay, so in such case, how do we estimate the one unstable manifold? Well, we could, for example, use piecewise linear or even higher order approximation of this density function, and then still try to compute the one unstable manifold. The part of the problem is that as you see, the gradients, once they manifold, these are all differential objects. So they're kind of sensitive to numerical order error. Okay, and also in general, simplification of such structure is not so trivial using even piecewise linear approximation. This has been done for two-dimensional. This is not too bad, but then when you go to three-dimensional and higher, this becomes much more complicated. Okay, so instead, we use something called a discrete Morse theory, originally proposed by Foreman. Now, discrete Morse theory is not a discretization of the smooth Morse theory. Rather, this is actually a combinatorial version, analog of the Morse theory, where the objects have become combinatorial. Okay, so this works in general for general cell complexes. Although in this talk, I'm just going to use triangulation. I think we have a simplicial complex where the elements are simplices, vertices, edges, triangles, tetrahedron, and so on. Okay. Foreman originally proved many beautiful results analogous to classical Morse theory. I will not give you a complete introduction later, but let me just point out that what we leverage is that this whole construction is combinatorial. So so in some sense that it's not really numerical. Okay, and later you will see that algorithmically it's very easy to handle simplification of the structures that we're aiming to compute. As I said, I will not introduce the discrete Morse theory. Let me actually only introduce the portion of it which is more relevant to explain the idea. Okay. In fact, I will not even talk about discrete Morse function. Rather, I would go directly to what is discrete gradient vector field, kind of analogous to the smooth case. Okay. So here our domain is a simplicial complex. So it's in this case we have a triangulation, vertices, edges, and triangles. Okay. Now, a discrete gradient vector now is not a real vector. In fact, instead, it's just a combinatorial pair. Okay, it's a pair of simplices, sigma and tau, where sigma is a face of tau of codimension 1. So it can be a vertex and an edge pair, or it can be an edge and a triangle pair. Okay, so you see this triangle incident on the edge. It's a pair of simplices where sigma is a face of the other one, codimension 1. Now, this is only a pair, this is only pair of simplices, but still you can imagine that this gives you the idea of flow direction. Say if I start from this edge, I can imagine that following this pair, I flow into this triangle. Then I can flow out from one of the other face, other edge. From that, I follow the pair and flow into this triangle. And I can continue doing this, and I can still get kind of a flow path. But the only difference is that now the flow path consists of a sequence of simplices. Okay, and such flow paths we call it V. Now, if you give me a collection of such pairs, this discrete vectors now, discrete gradient vectors. Now, this collection of pairs will form a valid discrete gradient vector field, kind of analogous to the gradient vector field in the smooth case, if the following conditions hold. Number one, every simplex should appear in at most one such pairing. This is just intuitively that at each simplex there should only be one gradient vector. Okay, so each simplex can appear in at most one pair. The second is that if you follow this V path, the gradient path that I was describing, a sequence of simplices following these pairs, then there shouldn't be cycle. All such V paths should be cyclic. This is because gradients, in general, you just keep flowing down. You can never come back up, so there shouldn't be cycle. Okay, so if you have these two conditions, then you get a discrete analog of the gradient vector field, which we call discrete gradient vector field. And those simplices that didn't appear in any such pair, okay, which are marked by the pink colored ones, like pink triangle, pink vertex, pink edge here. So these are basically, they didn't participate in any gradient pair of this discrete gradient vector. Then they are critical because intuitively the gradient vanishes there. So if you're there, then you don't know where to go. Okay, so those are the criticality. Okay, all right. So just a very high level, and here's very hand waving, not really precise. We now have this combinatorial objects, a discrete gradient vector field, which is kind of analogous to the gradient vector field for the Morse function. Okay, so intuitively, if you think that suppose we have a d-dimensional domain, suppose I have a triangulation of RD. So in this picture, I have a R2 here. Okay, so in this case, I have a triangulation of R2. And now, intuitively, you can think that the critical k-dimensional simplices, okay, they kind of corresponds to index k critical points in the smooth case. So in this two-dimensional example, you can visualize, you can imagine that critical triangles like this two pink triangle here, T1, T2, these are two-dimensional simplices. So they correspond to index 2 critical points, which are maximum. Okay, and the critical vertices, which is 0 dimensions, they correspond to the minimum. And the critical edges, which is 1 dimension, corresponds to index 1 critical points, which is saddle points in the 2-dimensional case. Okay, so you can still think that we'll have this relation. And now remember that earlier we were interested in the one unstable manifold. This is like that you go from maximum to saddle to maximum. Okay, the flow path connecting maximum to saddle. Now, in this discrete setting, the maxima is triangles, saddles are edges. This become the edge triangle path connecting critical triangles to critical edges, which are saddles. Okay, like this blue one, the triangle to this edge here. This is the one unstable manifold in this 2-dimensional triangulation setting. Okay, now, and this is what we would like to compute to estimate the mountain ridges. But if you have d-dimensional domain, then this one unstable manifold becomes simplices of dimension d alternating with simplices of dimension d minus 1. Okay, and this becomes harder to both compute and to maintain. Okay, so instead, let's now do a little trick. Let's instead of thinking about we have the density function, let's take the negation of that. So we have minus of the density. Now instead of mountain ridges, now I'm looking for the valley ridges, those connecting minima with saddles. Okay. Now in the smooth case, there's no difference. Okay, it's just the kind of a dual to each other, symmetric to each other. Now in the discrete case, now the advantage is that now the discrete structure you're looking for become the so-called one stable manifolds, which are this alternating path between vertices and edges connecting saddles, index 1 saddles with minimum. Okay, so now that means that to compute this object, I only need vertices, edges, and triangles up to 2-dimensional skeleton of your input simplicial complex. So your input domain can be higher dimensions, but I only need up to 2 skeleton of it. Okay, so that's what we're going to do now. We're going to instead compute the valley ridges. Okay. All right, there's one more thing about discrete Morse series that's very useful, which is the so-called Morse Cancellation Operation. This can be used to simplify the input vector field. In particular, what this is, suppose you're given a pair of critical simplices, like in this case, between V2 and E2, okay? If there's a unique V path between them, like in this case, I have this black V path here from E2 to V2, then you can cancel out this pair of critical simplices, namely make them not critical anymore, simply by kind of inverting the order along this V path. So if I just invert the order, then afterwards, neither V2 nor E2 are critical. Okay, so this is again analogous to the smooth case when you cancel a pair of critical points to smooth out the vector field. Okay, and you need the condition that there's only a unique gradient path for simplices, because otherwise, if there are more than one path, after inverting one of them, then you get a cycle. Then the resulting vector field is no longer a valid gradient vector field anymore. Okay, so basically what I said so far is that we have this combinatorial version of discrete of Morse series, And that we can have this discrete gradient vectors, which allow us to compute the one stable manifold. And we also have this Morse cancellation operation to help us to simplify, remove a criticality of simplices, which means that you can simplify the resulting one stable manifold structure as well. Okay, but which pairs of critical simplices should we simplify? Okay, and in fact, if you think about it so far in the discrete setting, I didn't even mention the density function at all. Okay, in general, you can simplify any pair of critical simplices as long as there's just a unique path between them. That's the only condition. Okay, which pair should we choose? Well, we should pretend, since in our case, we have this density function associated with the input, intuitively, we should simplify those critical simplices that are less important corresponding to respect to this density field, okay, kind of the noise. Okay, and to do that, I'm going to bring in yet another topological notion called a persistent homology. Okay, some of you may be familiar with this. I will not describe this in detail. Let me just give you a very simple, a real simple one-dimensional example to show the intuition. What is the persistent homology? Okay. Now imagine we have this one-dimensional real valued function f from R to R. I'm showing the graph of the function here. Okay. So now imagine that I'm going to sweep the domain in increasing function value. And when I do that, I track the connected component, the topology of the portion that I already swept. Okay. So here I have the value A, and then the portion I already swept at this two red part, and I track this topology in as captured by homology group. Okay, since in this case example, the domain is R, just a line. I can only talk about zero-dimensional homology group, which is just the connected components information. In other words, I'm going to sweep this domain and then track the connected components information. Okay, now we see that when we pass through a minimum, what happens is that we're going to create a new connected component. So we create some topological feature. So this x1 we consider to be a creator, and the same here at x2 and x3. At x4, what happens is that as we sweep past x4, the components intuitively created at x3 and the one created at x2 now got merged into a single one. So we reduced the connect components information. So we kind of killed the topology, the topological feature. Okay, so x4 is a destroyer, and then we pair up x4 with x3 to indicate that at x4, the components created at x3 got merged into a bigger one, so it got killed. Okay, so this pair x3, x4 indicates the birth and the death of topological feature, in this case, a connect component. Okay, so, and I can continue to do this, and then at x5, I kill the components created at x2 intuitively, and so on. In the end, I get this whole range of pairing of critical points. Okay, and each pairing indicates the birth and the death of some topological feature. In general, this can be higher dimensional feature, but here it's just the connect components. Okay, I can first plot this pairing into the so-called persistent diagram, where the x-axis is the birth time, the function value, like x2 is paired with x5, then I get a point which the birth time is a function value at x2 and the death time is function value at x5. So this point indicates the birth and death time in terms of the function value of your some topological feature. Okay, so just to summarize, if we have a function, okay, then we can perform this persistent homology procedure and the capture and summarize the results in this persistent diagram, which captures all the birth and death of topological features through this sweeping process. Okay, and we will have a piecewise linear function as what we have here, defined on simplified complex domain. This process can be simulated by something called lower star filtration, but then everything still works the same, and in the end, you get a collection of pairing between simplices now. Okay, and But still, you can think the same way. Each pair of the simplices, they actually indicate the creation and death of some topological features through this course. Okay, and the lifetime of this pair, just like the lifetime here between birth and death, is basically the function difference, the function value difference between these two simplices. Okay, so we can still do this persistent idea in the simplicial setting. Okay. So now we're ready to put everything together. Finally, I'm showing you the algorithm. So let's assume our input is a triangulation K of some domain I in RD, and we have a PL function given at the vertices of K and a threshold delta. Now I still do need a threshold to simplify the noise in your input function. Okay, so what we do is the following. There are only 3 steps. I started with a trivial discrete gradient vector field. Remember, discrete gradient vector field, a collection of pairs. Okay, so I started with a trivial one, namely I don't have any pair, everyone is critical. Okay, then I perform the persistent algorithm to compute the persistent pairing with respect to the function minus f. Remember, we change to the negative f in order to do the valley ridges instead of mountain ridges. Okay, so I compute the persistent pairing. Now the output of this persistent algorithm is that it pair up the simplices kind of with respect to the density function, and the persistence of them, the lifetime, tells me the importance of these pairs with respect to the density function. Okay, that's the intuition. Then in the second step, I simply look at all those persistent pairs, which are pairs of simplices, and if they're critical and if their persistence is smaller than my threshold delta, namely they're not important, and if they have unique gradient paths between them, then I cancel them out. So if I can cancel out the low persistent pairs, I do it. Okay, so I do the Morse cancellation, and I update my discrete gradient vector. Okay, that's it. And then in the last step, we collect the output. We pick all the remainder critical edges whose persistence is bigger than delta. Now remember, critical edges corresponds to index 1 critical points in the smooth case. So it basically now only saddles which large persistence, okay, persistence bigger than delta, and then we collect their one stable manifold, connecting them to minimum, and then output it. The output would be a graph. Okay, so the algorithm works for any dimensional domain, although we only need the 2 skeleton vertices, edges, and triangle of it. Okay, and here are some results of the reconstruction of the road network from the top right. The small picture, the blue ones are the input trajectories. So here's one from Berlin, and the bottom I'm showing the graph reconstructed at a different persistence threshold, and we can see that as we increase the threshold, only the major feature remains. Okay. I just want to point out that the main advantage is that because this is a global approach, you're using the global topological structure of your density field to decide the connectivity. So as we can see that output, usually the previous state of the art can be hard in making local decision, but here we see that the global connectivity is better captured. Okay, and this is the same algorithm applied to other imaging data for road network from reconstruction from satellite images or reconstructing neurons from 3D images and so on. Okay, so here I just want to point out that you can actually combine this. So here we combine this approach with units like architecture. To do a cell process segmentation of cells. The idea is that in these images, your signal sometimes can be very weak. The discrete Morse is good at capturing this topology and get over those weak signals. Okay, while the even with CNN, because it's not structure aware. Okay, this neural networks they're not really aware of the global structure in your images. Okay, they can miss those gaps, and then but the problem with discrete Morse is that it may also have a lot of false positives. So we combine the two together using discrete Morse to help to bias the neural network and then to get the final segmentation. All right, this is a more recent work where we're using this one to predict the so-called permeability for like images, 3D images of rocks. Those are porous media. They have kind of grains inside, and what you usually care about is the pore network. That's where the water liquid flow. And now typically people use CNN to do the prediction. But again, here really what you care about, because the water flows along these networks, this pore network connecting the empty spaces between the grain. So what we do is that we actually first use the algorithm I just described to get this representation of this pore network. This is 3D data, even though this example is 2D. And then on top of that, we use some equivariant GNN to do the prediction. Okay. All right. The algorithm that I described as it is only for low-dimensional domain because I need a triangulation of the domain. Okay, and this is not effective for high-dimensional data. Okay, if you have high-dimensional point clouds, then recently we observed that you can actually just thinking about the extend this algorithm to any filtration, okay, and then you can run this algorithm, run persistence, and then do this simplification and so on. In fact, this approach still has meaning, which your output in the end contains something called a lexicographically optimal cycles, okay? But nevertheless, so because of this new way of looking at the algorithm, you can combine this with the so-called sparse weighted RIPS filtration for point clouds data and make the algorithm also scalable to high dimensional point clouds. Now you don't need a space triangulation anymore, okay? All right, so these are the algorithm itself and some applications. In fact, we also have some theoretical understanding of this algorithm. Okay, why is this algorithm working? On the high level, you see I actually combine two objects, the discrete Morse theory and the persistent together, even though they're intuitively, it makes sense, but why should they really work as what we hope intuitively should work, okay? So in understanding this algorithm, actually first, we can significantly even further simplify this algorithm. Now remember that the current algorithm, the first step is we take this as a black box, okay? And the second step is that then we have to do this Morse cancellation for all the persistent pairs whose persistence is low, okay? And we have to check whether it's cancelable and then do the simplification, cancellation if possible, okay? It turns out that we don't need to do that at all. We don't have to maintain any discrete gradient vector field explicitly. Okay. Instead, we only need to collect certain edges, which turn out to form a spanning forest. Okay. So for those of you who know persistent, we're just collecting those so-called negative edges. Okay. And with persistent at most delta. So this edge, to do that, we only need a linear scan after the persistent computation, and then we get a spanning forest. And from this spanning forest, we can then retrieve the one stable manifold, which turn out to be just a union of certain tree paths together with some extra edges. Okay, so in other words, the algorithm now actually become very simple. Other than the first step, which is the persistent computation, computing the persistent homology, the algorithm takes a linear time. Okay, you just need to scan the edges and then do some tree traversal. That's it. Okay, so the algorithm, the total time complexity is linear plus the time to do the persistence. And this persistent computation, unfortunately, is the bottleneck. Okay, persistent is not easy to compute, although in the last 10 years, there has been a range of work devoted just to make the persistent homology computation efficient. Okay, there are different software, GoD, FAT, that's available to compute persistent homology more efficiently. Okay, and this result holds for any dimension. But from some implementation point of view, now the algorithm is very simple. It's just that you take off-the-shelf persistent computation software to compute the persistence, and then the remainder 2 steps, just a linear scan and so on. It's very easy to implement. And we also have a little bit understanding of what is the graph that we're computing. Okay, to do this, we have to give some have some more noise model to say how is the quality of the input density field. Okay, so you don't have to read here. So eventually our noise model is a pretty strong one, unfortunately. It roughly means that you have the hidden graph G, and then around the hidden graph there exists a small neighborhood omega. Okay, and your density input density field is such that within this small local neighborhood omega neighborhood of your input graph, your density function value is higher than outside. Okay, and the variation within and outside is also small. Okay, so within the neighborhood, the density is much higher than outside the neighborhood, and the variation is small. Okay, so under such a strong, this is a picture of this density field. Now, under this noise, this pretty strong noise model, we can indeed show that the graph that we reconstructed is geometrically close to the hidden graph in the sense that it also contained within this omega neighborhood, and it also has the same topology. Okay, so for two-dimensional case, when the domain is 2 dimensions, it's slightly stronger. That not only it has the same, because for graphs having the same topology just means they have the same number of independent loops. Okay, so for 2D, we can also argue that there's actually deformation retraction from the small local neighborhood to the graph we output. Okay, so in a way that the output indeed capture the geometry and topology of the hidden graph under this very strong noise model. Okay, now this noise model does not work. It's not non-uniform for non-uniform sample. Although in practice we do observe that the main advantage of this approach is that it actually works in the non-homogeneous setting. The part of the reason is because here we use the persistence threshold as the simplification, which is kind of measuring the relative density difference instead of absolute density threshold. Okay. All right. So this finished the reconstruction of the graph. Let me now just very briefly mention comparing and classifying graphs also using topological ideas. Okay. So here, so first actually, with the persistent homology I just mentioned to you, recently there's actually a line of work on using the so-called persistent-based, what I call persistent-based feature representation framework to compare, to classify objects. So say you have an input collection of objects, can be a collection of point sets, a collection of meshes, and in this case, it's a collection of trees. Each of them actually is modeling the neuron morphology. Okay, now to classify them, you can, for each of this object, you can first define some suitable descriptor function on top of that, and then use that function to map this object to a persistent diagram representation. Okay, now you can think of this as now you mapped this object, like this tree here, to a point in the space of persistent diagrams. Okay, and the collection of input become a collection of points in this space. Now, if you put a proper suitable metric on the space of persistent diagram, then you can carry out the remainder tasks, say SVM and so on, using this persistent summary representation. Okay, so it's a very generic framework and can handle different type of data. And now the choice of this metric on the space of persistent diagram is actually important. The original way to measure distance between two persistent diagrams, okay, they actually, one of them is like a Waterstan distance, so they're not easy to compute. They also lack the inner product structure. So starting from the so-called persistent landscape by Peter Bubenek, there has been a range of work kernel on the space of persistent diagram or map it to, a finite, map the persistent to yet another finite vector space so that you can carry out the, machine learning pipeline more easily. Okay, so here, let me just mention that we also, following this idea, we actually learn this metric using labeled data, try to learn the best metric for persistent diagram-based summaries in a data-driven manner. Okay, so this is with my student Zhao, and it's rather straightforward, the approach. Let me just show you it works. Let me just show the results that we compare with, at least at the time 2 years ago. This was all the state of the art other graph classification approaches, both from graph kernels and GNNs. And so our this learned persistent-based metric without using any graph attributes can actually achieve most of the time state-of-the-art graph classification. Okay, so this is to classify graph in a high level. In this case, it's a data-driven manner. But what if we want to compare graph at a more refined level? Okay, I want to have a distance measure between two input graphs. So let me here actually talk about the metric graph. Roughly speaking, metric graph is just a graph where you also have a metric structure induced by the shortest path metric on the underlying space of the graph. Okay, so considering the metric graph is not really limiting in any way, because any finite graph where with a positive edge weight can be thought of as a metric graph. Okay, you can think that each edge with the positive weight to be in a segment, a length segment of this length, say this one has length 9, okay, then you can define the shortest path, you can define this length of any path just by the sum of the length of all the segments in this path, okay, and then with that you can then define the shortest path, then you get the shortest path metric, okay. So now imagine that we're given two metric graphs, like these two graphs with positive edge weights, and we want to have a way to measure the distance or pseudo distance between them. Okay. Now, since now we treat the graphs as metric spaces, a natural way to measure distance between them is the so-called Gromov-Hausdorff distance, which is generally to measure how far two input metric spaces are away from bin isometry. Okay, and the Gromov-Hausdorff distance intuitively is basically looking for the best correspondence between the two metric spaces, so that under this metric spaces, the additive distance distortion is minimized. Okay, the maximum distance distortion is minimized. That's what the Gromov-Hausdorff distance is measuring. Okay, so it makes sense to use that to as a weight distance for the metric graph. But unfortunately, the Gromov-Hausdorff distance is very hard to compute. It's hard to compute even for two metric trees with unit edge lengths. Okay, it's still hard, and it's also hard to approximate with a constant factor. Okay, we do have with my former student, we do have a fixed parameter tractable algorithm to approximate the Gromov-Hausdorff distance for, but only for trees. For graphs, we still don't know what to do. Okay, there's a meaningful distance measure, but it's too hard to compute. So instead here, I'm going to talk about a simpler distance based on, again, the persistent homology idea. Okay, we call it persistent distortion distance. So the idea is rather simple. It's as follows. So let's say we have this input graph, this G1 here. Okay, for every point S in the underlying space of G1, so this point S here, okay, what I'm going to do is that I'm going to summarize how does the graph look like to the point S, okay, using a persistent diagram and map S to a summary. Okay, so how do I do that summarization? Well, given the point S, I simply consider now the shortest path distance function to this point S. Okay, so in other words, now the function value for every point is its value, its shortest path distance in this graph to this S, considered as to be the base point, okay, to S. Okay, so now I basically have a function now, and this function depends on the choice of S. Okay, so you can think of this function, shortest path distance function, to be how does the graph look like from a metric point of view to the space point S. Okay, and once we have a function, I can summarize it to be its persistent diagram summary. Okay, so this function, this f of S, can be mapped to this persistent diagram. That's what we do here. I take every point S, and then I compute this function, then I compute the persistent diagram summary of that function and map it to a point in the space of persistent diagram. Okay, and I do this for every point. And under this map called phi, the image of this graph is yet another graph, but now embedded in the space of persistent diagram. Okay, So what is the advantage of doing this then? And I'm just getting another graph. Well, this map is isometry invariant. It's very easy to see that. Okay. Unfortunately, it's not actually injective, but then it is injective in most places other than in discrete positions. Okay. Furthermore, even though that, so it's not only isometry invariant, it's also stable, this map. So if I have another graph, say G2 here, okay, in general, why is it hard to compare graphs? Because we don't have natural correspondences between them. They're not embedded in the common space. So what this is doing is that it just map each of the graph into this common space of persistent diagram, and this map turned out to be stable. So if the two input graphs house of sense, okay, then their image are close in the house of sense. Okay, house of distance is easier to compute a quantity, and this is exactly how we define the distance. So given two graphs, we find their map in the space of persistent diagram, and then we compute the house of distance between these two image set. Okay, house of distance is a polynomial time computable. Although in this case, it's trickier because I have this continuous structure. I have to see how to be able to use a discrete, only consider discrete number of points, yet still capture the house of distance. Okay, so that is the idea. So that's a distance. Okay, and one advantage of this distance is that it's actually a continuous distance. In this, what I mean is that it's insensitive to the discretization of the same metric graph. So if I have this red graph with red segment and the blue one, which they have the same length but different discretization, okay, a lot of other graph comparison, they actually compare the combinatorial structure of the graph. So then these two will not be the same. But from a metric space point of view, these two are the same. So and this is preserved by our distance measure. Okay, and it's also stable with this respect to the Gromov-Hausdorff of metric distortion in input graphs. Okay, I should point out that the previous one, for example, is useful when you compare road networks because maybe you have two maps which has a slightly different discretization. Some of them have certain small streets, some of them do not. Okay, all right. It's also stable, as I mentioned, and it can be computed in polynomial time. I didn't list the polynomial time here because actually the computation for general graphs is non-trivial. It involves computing arrangement of different hyperplanes and so on, and it's a high polynomial. Okay, for the discrete setting, it's more practical, but for the continuous case, it's not a very practical algorithm. We did implement it for the discrete case, so the code is available. All right, so let me just actually use 2 minutes to just mention what is the problem of the last one, and I'll wrap up. Okay, so here, so far, the two that I mentioned is more topological, and the approaches is more has more topological flavor. Okay, the last one is more geometric. The question here is that very often we nowadays handle graph data, and this you can view this graph given to us, the observed graph. You can view them as a noisy one skeleton of some hidden domain that you don't see. Okay, and then through analysis of this noisy graph, you want to retrieve information about the true domain that you don't see. Okay, so and suppose here, okay, what the information that we would like to recover about the true domain. Let's imagine that the graph actually there's a true graph underneath. Okay, and we got a noisy observation of that true graph, and we want to, the information we want to recover is the true shortest path distance metric in that true graph, but we want to recover that from the noisy graph. Okay, now note that it's not straightforward because graph shortest path distance is very sensitive to just some shortcut, some extra edges. Okay. But how do we model this? What is the true graph? What is the noisy observation? So here is our model. Imagine that there is a hidden domain of hidden space there, space M, okay? And imagine that the true graph, so let's say I have a hidden space. Here's a very boring circle, but it doesn't have to be. It can be, say, high dimensional, some remaining manifold, for example. So I have this hidden domain, that's a hidden space that we don't see. And imagine the true graph is generated as follows. We first sampled some nodes from this hidden domain with respect to a nice distribution on top of that, so uniform measure on this space. And we sample the points, endpoints, and then the true graph is actually the proximity graph spanned by these nodes. Say the R neighborhood graph, namely any two nodes within distance R will be connected by an edge. Okay, so let's imagine that this is actually the true structure that we're supposed to have, because this is the skeleton of this hidden domain to reflect the matrix information about this hidden domain M from this proximity graph, this R neighborhood graph. Okay, however, what we observe is not this graph. What we observe is the random perturbation of this graph. And there are two types of random perturbations. Now, with probability P, you could just randomly delete some edges. Okay, that's one. And then with probability Q, you can also randomly insert some shortcuts, like this green edges that you see here. Okay, and so this is the graph that's given to us with this perturbation. And our goal is to recover the shortest path metric of the original true, this our neighborhood graph. Okay, so that's what we want to do. Okay, now why do we take this model? Well, on a high level, you can think of this model, this observed graph, essentially it's like a Erdős-Rényi type of perturbation over a random geometric graph on non-Euclidean space, not necessarily Euclidean space, basically. Okay, so now we wanted this model. Basically, if you want to recover any information, you have to put some structure over both the space that you try to recover information and also the noise. Okay, so this is a natural way to model that space. Okay, so all right, and what we can show is that so this random deletion turned out that if you put some conditions on this measure that you're sampling from, say uniform, or it doesn't change very dramatically, then turn out the deletion is not too bad. Deletion is easy to handle. In fact, deletion doesn't change still. Even after you delete some edges, you can still recover the shortest path metric within the factor of 2, okay, with high probability. Insertion is the part that's harder, because random insertion, if you just add random edges, very soon you're going to reduce the diameter of your graph to constant. Okay, so the shortcuts is the one that can really kill the shortest path metric. Okay, so to handle those shortcuts, newly inserted edges, you have to do something to remove them. Okay, and it turned out that under this model, if we use a simple strategy called the Jacob index, which essentially for every edge it measures the edge similarity. It's a quantity that people use in practice to do denoising. And if you just use this Jacob index, then you can show that you can then, after this cleaning up, you can approximate the shortest path metric within a factor of 2 if the insertion probability is not too high. Okay, in fact, the insertion probability is we can handle is very small. It's almost like proportional to the average degree divided over m. Okay, but if the insertion probability is not high, you can use this Jacob index to handle that. Okay, if you want to handle more insertions, then you have to use a stronger object to help you to recover to figure out which are the bad edges. Okay, and in particular, leveraging the behavior of different behavior of Erdős-Rényi random graph and the random geometric graph, you can use clicks to help you to decide whether the edge is a false positive or not. Okay, so using the clicks, you can actually recover the shortest path metric up to almost a constant insertion probability. Unfortunately, the problem with the second approach is that the click is very hard to compute, of course. Okay, so it's the second one is more theoretical. The first one, the Jacob, is a practical algorithm. All right, so this is what I want to say. I guess, I mean, in concluding, sorry, I'm a little bit over my time. Let me just quickly summarize that. I think, especially to this seminar, I mean, we all agree that humankind has always interacted with the world through data, and mathematics, especially geometry, together with computation in ancient time, is hand computation, has been the language of science since for a long time, like the study of the celestial bodies in the sky and so on. Okay, but in modern days now, we are faced with the unprecedented availability of a different kind of data, low, high dimensions, geometric data, shapes, which is not so easy to handle before, and we're also given, but at the same time, a lot of computational power. Okay, so now this requires to rethink how we can better interpret and analyze data by combining computational methods with algorithms and mathematical models. Okay, and this group, of course, is a pioneer in this direction, especially using geometric method for graphics applications, for vision, and so on. And I hope that what I present you today also give you some ideas how topological method can also help us, especially with its power of summarizing, characterizing the essential structure behind data, can also help us in this endeavor. Okay, and with that, I thank you for your attention. Sorry, I'm 2 minutes over.
Okay, that's okay, of course. Thank you very much. Let's unmute and give Yusu a nice round of applause.
Thank you.
Now we have some short time for some quick questions. Does anyone in the audience have questions?
Hello? Can you hear me? Can you go over Morse cancellation a little bit more into detail?
Sure, yes.
Thank you.
So let me just go to that slide. So, okay, so in this case, you have the, so I mean, I'm only marking certain simplices here. So here, the red ones are critical. Okay, so we have actually in this picture, I have 4 critical simplices, V1, V2, E1, E2. Okay, but only let's consider V2 and E2. Okay, now there's, I didn't draw others, but assume there's a unique gradient path between them. And this gradient path is from this end point of E2 paired with this edge, and then from this, so that's one pair, okay? And from this vertex, it's paired with this edge. So this gradient path has 2 pairs, yeah? And the V2 and the E2, they're not in any pairs, so they're critical, okay? How do you now cancel them out?
It's not in any path, sorry, not pairs. I'm sorry, I didn't.
Right, so this is the connecting them through V-path. V-path has to be alternating between pairs of, I didn't define that formally, that's why. It has to alternate between critical, this pair of, this discrete gradient vector. So you, so how does it work? You follow the discrete gradient vector from this vertex, you follow that, you go to this edge. And then you go to another face of this edge. There's only one choice, it's this vertex.
Oh, okay, okay, so you make a decisions.
Exactly. Yes. Yeah. So if you have such a path, then how do you invert that? So now, after I invert in this case, I simply says, okay, this edge. Remember, this edge used to be paired with this vertex. Okay. Now it simply says, now this edge I let it pair with V2. That's why you see the direction is also changed. Okay. So this edge is now paired with V2. Then this vertex now paired with this edge. Now this vertex become free. Because it's free, you can pair with this E2. So afterwards, you see you have a gradient flow now from this saddle to all the way to this vertices. So you get a, so that's how it works.
Okay, thank you.
Any other questions? Well, I have 1 or 2 questions. You mentioned earlier you had you stated a theorem about the running time of the algorithm. I think that you mentioned that the bottleneck was the time needed to compute the persistence.
Yeah.
Yes. Can you give an idea about how much time this
Sure.
usually takes?
Yeah, so the persistent computation asymptotically takes time n cubed, where n is the total number of simplices. Okay, and the best theoretical bound for compute persistence is n is the matrix multiplication time. So you can improve from n cubed is just coming from Gaussian elimination. Persistent computation essentially boils down just to do Gaussian elimination in a certain way. Okay, but you can use matrix multiplication, faster matrix multiplication, so you can bring down this time to be n to the power of 2.37 and so on, but nobody implements that. However, in practice, okay, what's observed is that especially in low dimensional case, the persistence, you tend to be closer to near linear instead of going to the n cube. Now, but in the worst case, there's actually theoretical bound saying that it's matrix multiplication time under a certain model. What's been done in the past many years is that there are a lot of tricks added to the persistent computation. So the standard, as I said, is just like a Gaussian elimination. You start with the so-called boundary matrix, and then you do certain column operation. And then people say that, okay, we can also do this kind of do the operation in the dual space using cohomology and also do row operation, and then those combined can make it more efficient empirically. Everything's empirical. So unfortunately, the asymptotically it's matrix multiplication. So if your input is only a triangulation of two, okay, if you only care about zero-dimensional homology, then that's very easy. It's unifying data structure. It takes only n log n plus n alpha n. Okay, and if your domain is a triangulation of two manifold, it's also n log n. So those are the easy case, but in general, unfortunately, that's not. Even in our case, we only use the two skeleton, but your domain can still be high dimensional. That's why you don't get this n log n time complexity.
Okay, thanks. And I was also puzzled by the statement that except this bottleneck, the complexity is only n, where n is the number of vertices and edges. But in a high-dimensional space, there might be a lot more simplices of higher dimensions.
Right. So this algorithm number one, to compute, since in the end we only compute the so-called one stable manifold. Number one, we don't care about the dimension of simplicity beyond two. Okay, so you only need the two skeleton, vertices, edges, and triangle. Now the triangle is important in the computational persistence. That's why the time complexity for persistence actually will depend on big N, where N is the number of vertices, edges, and triangle to the cube or 2.37. Okay, but once you finish the persistent computation, you don't even need the triangles anymore. Okay, the remainder, the information that we want to retrieve can be just retrieved from only the edges and the vertices. That's why it's only linear, depends on vertices and edges.
Okay, I see. Are there any other questions? If not, let's thank Yusu again for an extremely interesting talk.